They would get the review set.
I did it that way for G2, and we did my G1, G2. Future values.
I walked up to it and I was like, yeah, so you can tell me what kind of solar price, I just couldn't, I don't know.
I wonder if that's why I can imagine that. You go real here and imagine something here. If it's like 4.5,
sometimes I just want to try.
right before that,
Yeah, you want to do that. You want to be I mean, if you're a computer, go for it. Don't mind. If you're not, hydrogen would go.
So, first, questions about prior homework? 628?
Yes, sir. Had some issues with whether or not to include,
Why don't we, go ahead, just say, Robert, we'll get it.
it says assume distilled water, sigma equals 10 to the minus 4 cm per meter. Epsilon relative is 31.
Minus 4, okay.
Epsilon relative is 31. Mu relative is 1. Fills the region Z greater than 0. At the surface, we have E of 0 and T.
What's that?
E of 0 and T is 8 cosine.
Okay, so it's 8 cosine, go ahead.
2 pi times 10 to the 8 T.
2 pi times 10 to the 8 t, go ahead.
AX volts per meter.
AX?
Yes, sir.
Okay.
And it wants to find E of Z of T, so the generalized form, H Z of T, and power average and power passing through a 10 meter squared surface located at Z equals 1.
Alright, so it's saying that this doesn't have any Z variation, is that what you're saying?
That's
That's-
E at 0.
Does
That's
have.
E at 0.
Zero.
At Z equals 0, okay. Go ahead.
And it wants us to find like a generalized form.
Form for E of Z, so it wants E, it's saying this is what it is right here, the surface, this is, and it's in the AX direction, so this is X. E field's like this, so we have E field versus time at this point. Now they want to know what the actual formula would be for it inside this region. This would be where the actual distilled water is. Do y'all follow me on this? So what we have to do, you've got to go ahead and get alpha and beta, so we need gamma, that's the first thing. And you remember that gamma is equal to alpha plus j beta, and that's equal to the square root of j omega mu times sigma plus j omega epsilon. Now, I'm going to get to this in a second, but looking at this equation right here, what can you tell me about omega just by looking at it?
2 pi times 10 to the 8.
You all see this class, 2 pi times 10 to the 8th, and that would be radians per meter. It's the coefficient of t inside a cosine argument. Y'all follow me? Everybody on this? Next, let's get that marker. Use this for a second. Now we have sigma, and we have epsilon relative is 81, right? One thing I'm going to do over here, I'd like to see if it's a good conductor or not. It may not be. So, if we take a look at sigma, right, over here, we're going to take a look at that versus omega epsilon. Now, if this is much greater than 1, it's a good conductor. Y'all follow me? The reason is sigma dominates, right, and omega epsilon is the displacement current. So let's just take a look at it. They give you sigma is 10 to the minus 4, right? And then when we take omega, which is 2 pi times 10 to the 8th, then we have have epsilon relative of 81, and then you have to multiply it by 8.854 times 10 to the minus 12, because that's epsilon naught. Tell me what that ratio is. Anybody? Yeah, I appreciate when people work along with me. I'm just gonna see if it's a good conductor or not. I don't know. If it is, I'm gonna change something over there. I can ignore the omega epsilon, but maybe I can't. Is it hot in here? This is usually a frigid room, so I don't know what they did. In the summer, I'm telling you, I taught in here in the summer. Was anybody here in my summer classes? It was ice cold.
2.22 times 10 to the minus 4.
Okay, what does that tell you?
Not a good conductor.
2.22 times 10 to the minus 4. That means it's really pretty good insulator, correct, class? We probably, and I say this almost hesitantly, we probably can ignore the sigma term here. Right? However, I'm going to put them both in just to see. I think you can, though. That's small. That's very small. So, is that right, by the way? What he just gave?
Yeah, that's right.
Okay, so if that's right, that is not a good conductor at all right now, not at that frequency anyway. So I'm going to go ahead and get this, and we're going to find out it's primarily going to be just J beta. Alpha is going to be very small. So if you put it into here, J times omega, which is 2 pi times 10 to the 8th, times 10 to the 8th, then times mu naught, and that's really 4 pi times 10 to the minus 7, right there. It's going to be that. Then I have to take sigma, which is 10 to the minus 4. You probably can ignore that, but I'm not going to right now. Plus j, and then omega, which is 2 pi times 10 to the 8th, and times 81, and then times 8.854 times 10 to the minus 12. And if you do that, remember that square root. Give me what alpha and beta is. Alpha is going to be small, beta is going to be large. I can't tell you just by looking at this. When I do these, I use MathCAD. MathCAD is what you see is what you get. I can plug the things in. If I alter anything everywhere in all the equations I have, it's automatically changed. So it lets me zoom through these problems. I'll show you that sometime now. What would you? MathCAD. Matter of fact, if I have a chance today, I'll put it up because you'll thank me. It makes homework go so fast, much faster than using, I mean, I suppose there are probably some tools that are equivalent nowadays, but it's much better than MATLAB or Mathematica for doing things, because I change one thing in an equation at the very top, it changes all the other things immediately, and it doesn't require me to run the program. Yep.
Is that 4 pi times 10 to the negative?
Minus 7. That's mu naught. It's just mu naught. Now the constants like mu naught, you should know them pretty much. Mu naught's 4 pi times 10 to the minus 7. Epsilon naught, some people render it as 1 over 36 pi times 10 to the minus 9. I usually just write it as 8.854 times 10 to the minus 12. Speed of light is about 3 times 10 to the 8th.
I just read it as 3.
What?
I just read it as 3. I was confused.
That's
Yeah, the 7.
Oh, sorry. I make French 7s. There's a long story behind this, but
I got .00209.
0.00209 plus
18.86 J. Plus J 18.6.
Anybody else? You got that? All right, I'm betting it's right, but you can see this is a very low loss dialect. The alpha is just about negligible compared to beta. When the two are about the same, then you got a pretty good conductor. All right, so we have this for gamma. Now, the next thing we need, because we want the full equation, he wants H field too, right? All right, now we need eta. So eta, we're going to do the whole 9 yards on this, but you're going to see it's just about strict real. If you do this, it's going to be square root of j omega, which is 2 pi times 10 to the 8th. and times mu relative, which is, I mean, this is just mu naught, which is 4 pi times 10 to the minus 7th. And then it's over sigma 10 to the minus 4th plus j omega 2 pi times 10 to the 8th times 81 times 8.854 times 10 to the minus 12. And if you go ahead and do this correctly, that's all under there, you're going to get about a real number. It's going to be about real. Matter of fact, the number you're going to get is about 120 pi divided by 9. It'll be about that. And I know that because the square root of epsilon relative, square root of epsilon relative, where 81 is 9. And this is going to be about 120 pi by 9. Pardon? Is that what you got? For this equation? The whole equation, or just what I asked you to do? Okay. Say it again. 41.9 at 0 degrees?
I was just kidding. I did.
Oh?
Never mind. I did different.
Okay. Well, if you just take 120 pi, or 377, and divide it by 9, what do you get? Just tell me that. 41.9. All right? It's about that, but it will have a small, but not 0 angle. It'll be a very small angle. Okay.
0.01 degrees.
All right, we're going to ignore that 0. We're going to call that, okay? Now, we have the E field, general form of the E field. We're assuming this is just below the surface. We're not assuming it's striking the surface because we haven't done reflections yet, so we can't do that part as well. So to get this part, this equation, now I've got alpha, I've got beta. Does he want the phasor form or time domain?
Time domain.
So if he wants the time domain, we have to make one assumption. He's got no offset in phase. This is for z equals 0, okay? So now we can say, in general, the E field has to have the form of some E naught, e to the minus alpha z. Just remember that has to be there. Then it's going to be times cosine of omega t minus beta z in the ax direction. That's the general form we're going to fit it for in the time domain. Y'all with me? Now, he says when it's at 0, it's this. So we already know 8 is the coefficient, the magnitude. Y'all follow me on this, class? He gives us that, so I can just make this 8. Now, the next thing I need to do is put in alpha that I calculated, somebody calculated. It's 0.0209, right? So I'll just put in alpha there, and it's really going to be, call it 2.09 times 10 to the minus third z, okay? Now, omega we got, y'all follow me on that? I'm just replacing the things. We know omega is going to be equal to 2 pi times 10 to the 8th. Now we put in beta. We got beta is 18.86 z, right? Y'all with me? And that would be in the AX direction. That is going to be the actual E field of volts per meter. Is that the answer he gives, by the way? Can anybody confirm or deny?
Yes.
Okay. So y'all follow me how I did that. Constructed it based on this information to get omega and the magnitude of the E field. To get alpha and to get beta, we had to do that calculation. Got it? Because there's time harmonic constant frequency. Now to get the H field, all right, really we could render this in the phasor domain, and I usually like it in the phasor domain. In the phasor domain, this would have the same magnitude of 8. It would be e to the minus, and I'm just going to leave it as alpha z. Alpha is that number. And then it would be times e to the minus j beta, that beta, z, in the AX direction. Do y'all follow me on that? I'm not writing alpha and beta down. They're already stated above. Y'all follow me? Can you all see it in the back too, guys? All right. Now I'm going to just use that clever little trick, because it's propagating waves, to get H. And I'm going to get in the phasor domain. H is gonna be 1 over eta, there's my eta, right? 1 over eta, unit vector in the direction of propagation. Nobody up front answered. What is the vector, what is the direction of propagation? Just look at it. None of you guys.
Let's see.
It's the positive z direction, so unit vector in the direction of propagation would be az. Got me on that? So it would be times az, that's where this is 1 over eta, unit vector in the direction of propagation, crossed into E field, crossed into this. 8 e to the minus alpha z, e to the minus j beta z, and the ax direction. I'm showing you how I would recommend you get familiar with doing it. And this is going to be called 8 in that region. I'll put down the actual value in a second. Now, just by inspection, since that's strict real, right? I mean, 8 is about, yeah, it's got maybe tenths of degrees, but we are going to ignore that. AZ crossed AX is AY, right? So I get this is going to be equal to, it's in the AY direction. Then I have 8 over 80, 8 over whatever that is, 41.9, right? It's going to be e to the minus alpha z, e to the minus j beta z, and this would be amps per meter. This is in volts per meter. Now remember, this has the units of ohms. So volts over ohms are amps. And can you just give me the actual magnitude of that? 8 over 41.9? See if it's right. What is it? 191 milli? Is it?
0.1.
Okay. 0.1, oh, how about 190? 191, right? Or 190 milliamp per meter? Right, in magnitude? Call it that. And this is going to be times, of course, e to the minus alpha z, e to the minus j, beta z, and it is in the AY direction. Okay? I'm just trying to show you that this would be in the phase domain. How do you get it in the time domain? The only thing I'm going to do is what? I'm basically going to copy this right here and just divide 8 by 41.9. Follow me? Has the same exact time domain signature. There's no added phase here because the angle on this, on eta is 0. You follow me? If eta did have a different angle, then that would have to be incorporated up here. Got me on that, guys? How many see this? All right. Other questions? Good question. Yeah. Go ahead.
Well, when I was working through it, I was confused as to whether or not I could ignore the imaginary part of data and the sigma.
Well, I mean,
it was like, to me, I thought sigma wasn't, or sigma versus omega.
you need,
I thought it
to
wasn't.
get alpha, you have to use sigma, all right? I mean, Whitmer test, I'll just tell you this, in Dr. Whitmer's book, he has something, when you have a low loss condition, you can get an approximation for alpha, right? It's, in my opinion, it's much easier to just use this equation and not to worry about anything else, because this will give you the value of alpha and beta all the time. You'll never mess that up, right? Regardless of how small sigma is or how large sigma is, you'll get the right answer every time if you do that. He has some approximations that I never use.
So how would that work if you took into account the small imaginary component of data?
All right, he says, suppose I just give this a fictitious angle, right? I'm going to give it an angle of, say, 10 degrees, okay? Now, think about that. When I come back over here to this equation, remember, this is fictitious. I would say this would be 1 over eta. Now, eta has a magnitude of eta 1, and it's got an angle e to the j 10 degrees. I'm leaving it in degrees, right? Now, what happens when I take this upstairs? That becomes e to the minus j 10 degrees, right? E to the minus j 10 degrees, right? Now, what happens when I lump this stuff together? Now, can you see that these two both have the minus j term, right? So these two would become e to the minus j quantity beta z plus 10 degrees. And it really should be in radians. I'm just, because beta is in radians per meter times z is meters. So this is radians, it should be radians. Maybe I'll do it this way. Pi over 20. So I won't add to the confusion that if you have Dave Irwin's book, a lot of times you'll see cosine of omega t plus 10 degrees. When you turn it into a phasor, it's just a magnitude at 10 degrees. Well, frankly, 10 degrees there should never be next to omega t, because omega t is in radians, right? But that's another story. So now I get it down to this point. You with me? So now I have that up here for those two terms. I have b to the minus j quantity beta z plus pi over 20, and the a y direction. To go to the time domain, the only thing I'm going to do, I'm going to have 8 over the magnitude of 81, still whatever that is a scalar value. Then I'm going to have my e to the minus alpha z here, but then to go to the time domain, now it's cosine of omega t minus that beta z, right? Minus pi over 20. So that's how that angle would work in there.
But for this problem, it was so small, we just didn't.
It went at about 0. Usually
Point
it's,
zero.
all right, so we just, there comes the point we just ignore stuff. Okay, other questions? Good question. Good problem, too. Yeah.
You don't want to take time for this.
No, just, if you
The
got
first
a question,
problem,
I'm gonna be.
not to solve the problem, but you were asking about the AC resistance in a wire.
Okay,
And I was trying to figure out just about like when you have, typically when we're talking about power, that when
AC.
you have when you have a wave that's incident like a slab of metal,
Yeah.
you see it kind of dwindle down.
Well,
And then you have that with the wire, right? So which way is when power's coming into a wire, you have an AC current flowing along, you just kind of get a visual what the fields look like.
let me tell you, what he's talking about is something that confuses people all the time. I'm just gonna draw an oversized wire like so. Alright? Now, assume it's a good conductor. It has to, right? When we actually develop a voltage, if you take a look at this, there's something we talk about, first of all, if this is a radius A, and if A is something we always compare to the skin depth. So if the skin depth, right, is much less than A, and that's the skin depth is equal to 1 over square root of pi f mu sigma. What that means is all the current is going to be on the surface of the wire. Now this gets a little weird. So I know I have current flow this way, right? But really, it's not going to go down the center of the wire. It's not uniformly distributed. All the current is going to be contained within one skin depth of that cylinder, the outer cylinder. Now, when power's flowing, there's an electromagnetic wave. Remember, this right here is usually part of a two-conductor system where you have another wire down here where you got return current. Follow me? And you're going to have an electric field that's going to be outside here, and a magnetic field, and that will really be the thing that's going to be propagating at the speed of light, or if there's a dielectric, at the speed the dielectric allows it. And there'll be a wave, there'll be an electric field this way down to the other wire. That wave will be propagating at the speed of light. Follow me on that? But there's also a component of the electric field in the direction of the current. Trust me on this one. That electric field actually decays very rapidly in here, and it causes currents to flow. The actual power flow in the wire is going from the outside inward. So, yeah, and that means this power flow is going to have a very small velocity inward, but it basically dissipates that. Now, the common way of thinking about this with DC is we got current going this way, the power flow must be going this way, but that's wrong. Because power, as you saw, was E cross H, right? You all remember that? Well, if the E field is in this direction, right, and the H field is basically going to be in the azimuthal direction, E cross H is into the center of the wire. That's the way the actual power is propagated. But there's an electromagnetic surface wave that actually contains the energy that goes downfield. And we're going to get into more of this in a bit, but I'm trying not to cause too much problem. Remember, power flows from the outside of the wire towards the core if it's being dissipated, or if you're looking at the wire resistance, that's how it does it. And Whitworth has an example of that in his book. He works through it, where he talks about calculating the power dissipated in a wire. Did you look at this, anybody? Anybody know? All right, if you get it, I would recommend you do that, because in there, then it becomes clear what's going on. But it's a little, I don't know, nebulous would be the way for me to describe it. That's a good question. Yeah, he's got it. What page is that on? Right there?
343.
Page 343. That's it. All right. Other questions about the homework or about anything? Because we talked about power, about AC resistance. Did you do those problems where I had AC versus DC resistance? Y'all see what I'm talking about? How many tried them? At least be honest with you. I encourage you to do that. Stay with this, because Friday's getting a quiz, so you really have to make sure you kind of keep up with this stuff. It can really scald you if you don't keep up with it. I'm just warning you. Okay, next. Today.
I got a question. So, 630, there's just the equation for eta. I don't know where it came from.
Why don't you give it to me, we'll see what we can do. This is problem 630?
200 megahertz with no plane wave,
200 meg.
incident on a thick copper slab imparts a 1 millivolt per meter.
This is copper? Okay. Go ahead.
1 millivolt per meter amplitude at the surface.
Okay, so he gives us the E field as 1 millivolt per meter, right?
How much power passes through a square meter at the surface?
Okay. Now, here we go back to the power equation. First, remember when we did power, we said the average, and this is going to be average power. Average power is going to be 1/2, right, times the magnitude of the E field squared over eta, magnitude of eta. Then it's going to be times the cosine of the angle associated with eta. Remember for that last one, I made it the fictitious pi over 20, right? And a good conductor, that angle is 45 degrees. Remember that. And then it's going to be times e to the minus 2 alpha z. And this would be in the AZ direction, by the way. Now, you asked this question, so I hope I'm answering it piecemeal. That's the equation. Right? Now, if we have copper here, copper has a conductivity, it's in the back of the book, of about 5.8 times 10 to the 7th, 1 over ohm meter, or Siemens per meter. That's huge. It's an extremely good conductor of room temperature. So now we have to find, without a doubt, we're going to ignore the epsilon, the omega epsilon term for the conductivity, or for the impedance. So now to get the impedance of this, that's simply equal to square root of j omega mu over sigma. Better yet, because square root of j is just j is e to the j pi over 2. The square root of that is e to the j pi over 4, or 45 degrees if you want it in degrees. So this is really going to be a magnitude of square root of omega mu over sigma, and it would be e to the j, if you want it in degrees, 45 degrees. We can leave it like that. So can you give me that omega mu over sigma? Mu is just mu naught. There's sigma, and omega would be 2 pi times 200 megahertz. Did you do it this way?
The solution gave.
Don't worry about the solution. But did you try it this way or not?
I did it that way, but then I used the solutions equation for eta.
This is it. It's the same thing.
Okay.
I mean,
That one
this
looks
is
more familiar.
this is a very good conductor. Trust me on this one. So go ahead and do this. So this would be what? Square root of 2 pi times 200 times 10 to the 6th, right? Oh, times 4 pi times 10 to the minus 7, right? And that's over sigma, which is enormous, 5.8 times 10 to the 7th. And it's e to the j 45 degrees. So give me that magnitude if you don't mind. Anyone? I'm looking at that. I'm seeing something so small, it's like milliohms, I think. And I appreciate you guys doing this, working with me on this one. Remember, omega is just 2 pi times f, it's 200 megahertz. Mu is just mu naught, 4 pi times 10 to the minus 7. Sigma is 5.8 times 10 to the 7, massive. What'd you get for?
5.2 milliohms.
That's about right. So it's 5.2 milliohms times 10 to the minus 3rd ohms, and it's at an angle of 45 degrees, or pi over 4 radians, right? Now keep watching this. So we've got that. Now go over here, this power would be in watts per meter squared. It's the power that's flowing per meter squared. So take a look at this. It gives us, this is 1/2. The E field was given as a millivolt per meter, so it's really going to be times 10 to the minus 3 squared over eta, which is 5.2 times 10 to the minus 3rd. Now remember, I'm just putting the numbers into that equation, but we have to get the cosine of that. It's the cosine of 45 degrees, which is 1 over square root of 2, or 0.707, about 70%. I'm just going to multiply this by 0.707, and then it's going to decay as e to the minus 2 alpha z, but he doesn't care about that. He just wants the power flowing through a meter, right? A meter square meter. So this is the number he wants. And what do you get for that? How many see what I'm doing right here? You understand it? You guys? No? I'm asking, I'm going to always go to you. He's the quiet one, but he's always looking at me suspiciously.
Where did you get the theta from again?
Remember this angle right here, 45 degrees? That's the angle. It's the angle associated with the characteristic impedance. So this is 45 degrees, isn't it? You with me? That's where it comes from. It's the,
And that's in, you just convert it to radians?
well, it doesn't matter. You can take cosine of degrees, 45 degrees, or cosine of pi over 4 radians. It'll give you the same value. Remember, the angle is the angle associated with that impedance right there. That's what that cosine of theta sub n, or eta, it means.
Got 68 milliwatts.
68 times 10 to the minus 3rd watts per meter squared. And if it's times some square meters, just watts, right?
Yeah.
Is that what he has? His answer? In a book? No?
I got 96 micro.
He didn't multiply it 27.
He has to. If he didn't, he made a mistake. That has to be there. All right? If this is the electric field in the material, and you want to know how much power is flowing here, it has to have that. You're telling me he didn't multiply by 0.707? That's a mistake in his book. As a matter of fact, I had dinner with him last night with a candidate, and he mentioned to me, he said, you always point out mistakes in his book. Now I've got another one. If we were telling this true. Is the answer wrong? I mean, is this?
Yeah, he did.
He's got 96 microwatts.
Hold it. Can anybody confirm that this is the right? If you just take, forget this.
I didn't square on top.
Yeah, the units are wrong.
What is the answer?
68 microwatts.
Is that correct?
Yeah.
Is that in the book?
The book says 96, because it didn't multiply by.
68 times 10 to the minus 6 watts. I'm going to tell you that nobody's perfect. His book's pretty darn good with the solutions and stuff, but they'll make mistakes. Has to have that there. Has to. It's a good conductor. Okay? Did you catch that one?
I didn't.
All right. It's all right. Are we good on that? All right, that's a good question too. So now, any other questions before I move on? All right, today, let me tell you what I'm planning on doing. I want to go through polarization, but I'm going to do it my way that's easier to understand. And I'll tell you the key thing about this. Then I'm going to go through reflection from really where you have a surface reflection from a normally incident wave. That's my goal today, so I'm going to see if I get through it. All right. Next. I'll use this one for that. All right, so we're talking about polarization. That can mean a lot of things to a lot of people. here's what we mean when we talk about electrical and computer engineering. If you have an electromagnetic wave, and assume it's propagating from here in that direction. I want to try to give you a visual of this first. If you have an electromagnetic field, it has a certain orientation and a certain direction of propagation. The orientation of electromagnetic field will always be perpendicular to the direction of propagation, always, for a propagating wave, in free space, or in an unbounded region. The H field will always be perpendicular to the E field and the direction of propagation. As a matter of fact, E crossed H will give a vector called a Poynting vector in the direction of propagation. All right, so that's what always happens. Now, if you have an E field that's polarized in this direction and propagating in that one, if you just froze space called z equals 0 and plotted the actual length of the electric field vector, you would see the thing get bigger, go to 0, go negative, get bigger, and it would trace out a straight line. Does that make sense to everybody? So the tip would trace out a straight line. That's called linear polarization. Linear polarization can be in the vertical direction, just tracing out a straight line, horizontal, or at any angle. But the idea is that the electric field will go to a relative maximum, then to an absolute 0, and then to a relative minimum in the opposite direction where the maximum occurred. Y'all follow? That's linear polarization. You can also have a wave that has two components, an E field in the vertical and an E field in the horizontal direction, propagating that way. Now, if the two are in phase, it'll just draw out a diagonal. It'll be linear polarization that way. Y'all follow me? The tip will increase, at a maximum go to 0. However, if there's a phase difference, especially if the two magnitudes are the same, and there's exactly 90 degrees phase difference, then the tip of this electric field, if you take the two and sum them, they'll always have the same magnitude, and the tip will trace out a circle, and you hold Z constant. That's called circular polarization. Does this make sense to everybody? And I'll show you the visual on the board. Now, the way they distinguish different types of circular polarization is what they call the handiness. So, if you want to know if it's a right-hand or left-hand circularly polarized wave, you take your right hand and you put your thumb in the direction of propagation and your index finger in the direction of the field. And if the field, as time increases, rotates in this direction, it's called right hand. Guess why? Because it's like opening a door with your right hand. Right hand circular polarization. However, if it goes in the opposite direction, it's called left hand circular polarization. Does this make sense? This is not hard, but this is the real reason it's so important. So if I do radar work and antenna work, but primarily radar is where it becomes interesting. If I send out a right circularly polarized wave and it hits a conducting body, it reflects back left-hand circularly polarized. Now, there are things called polarization filters where I can sift out and only allow left-hand waves, left-hand circular polarization waves to come through, as well as for a given frequency filter. So I know if I get a left-hand circularly polarized wave return from after I send out a right hand, they're in bursts, small bursts, at the frequency I sent out, pretty much there's something out there that reflected it. And from the time of flight that it takes to go out there, hit that, and come back, I can reduce the range. Y'all follow me? That's the real benefit of using right-hand circular polarization or left. There is also something with weather radars that I don't do a lot of, but I know. Big problem, you'd like to know as much as you can about the storm without getting into the storm. So radar is the ideal way to do it if you know what you're doing. And you gotta understand something. When you have storms, it's not just droplets of water that look like teardrops. There's part of it. There's also a thing called grapple, which is slush, and there's hail. All these things have a unique return, and there's also a wind field out there. Raindrops sort of look like a teardrop. They're long. They're elliptically long. So what you can do with a weather radar is you can get an elliptically polarized wave. And if you orient this thing, change the orientation versus time, and when you get that maximum reflection back, that tells you the orientation, primary orientation of the actual droplets that are falling. Y'all follow me on this? So if you got something that's like, I'm going to exaggerate, say a raindrop that's falling in a wind field this way, and it looks like this, when all of a sudden that elliptic polarization is in this direction, they use elliptic for that reason, to get the maximum return, they know about the actual angle these things are moving in the relative size. There's a lot to this, but that's the reason they use elliptical polarization. They'll get the same time delay, and if they send out right hand, it'll come back left hand, but that's the reason they use that. Now, we live in the South. Tornadoes, they happen about at least a couple times a year down here. You have some kind of tornadoes. Huntsville, they get bombarded by them. And there are places that they have tornadoes expected a couple of months all the time. Thankfully, we haven't had any bad ones in a long time. But with that in mind, what they do is they have these radars that look for what's called a hook echo, a Doppler hook echo. Have you ever heard of this, Evan? All right. Their Doppler radar, which means they know the actual velocity, the differential velocity of the particles, as well as the range and the relative magnitude. Now, all that is very interesting to the military and to, I think, navigational systems like Atlanta Airport and stuff like this. But it's not my area of specialty. I'm just telling you what I know about that. I'll tell you more about radar when we get to it. But all these things use polarization. So in general, here's how you do this. We're going to say, I'm going to let z equal 0. We're going to assume the wave is at z equals 0. We're all going to be looking, we know it's going to be propagating the plus c direction. I'm just going to take a look at two components of the field. I'm going to plot Ex on this axis and Ey on this axis. And I'm going to say that the total E field can be rendered as some E naught x, or E naught x, times cosine of omega t and this is going to be ax, of course, plus some E naught y cosine of omega t plus phase angle ay. Now, I'm going to start by saying the phase angle is 0. So that means my E field here is going to be some E0x cosine of omega t ax plus E0y cosine of omega t ay. Now, if you look at this thing and you do a plot of just the vector, the tip of the summation of that vector, just take a look at this. When omega t is 0, it's the way you do it. You assume omega t is 0. Here it's going to be just E0x ax plus E0y ay. What that means is, out here I'm going to have a vector length here of E0x and a vector length here of E0y. It means the tip of that vector would be there. That would be point 1. Do you all follow me on that? All right, now let the phase angle increase. If you let omega t equal to, call it 45 degrees. All right, well now I have cosine of 45 degrees times E0x. Cosine of 45 degrees is 1 over square root of 2. You all agree with that? Plus E0y cosine of 45, which is 1 over square root of 2. What really happened is now the tip of this vector is going to be down here, right? And what you can see is this vector is going to start decreasing in size until it gets down to 0. You all follow me? Then if you let time progress, the only thing that's going to happen is it'll increase in size this way, and it'll go to there, and then it'll go back and forth, back and forth. You all follow me? That's exactly how you plot these things. You just find out, they'll give you an equation, turn it into a time domain equation, let z be 0, and take a look how the tip of that vector moves. You have to calculate both the x and the y component, and then plot it. So this is the point where the first one is. Second, third, fourth, goes to 0. That's linear polarization. If you really wanted to be exact about it, you could say it's at a certain tilt angle. I never asked that. That tilt angle you can calculate just by basic trig, right? That tilt angle would be what? It would be the opposite, or it would be EX0, or it would be adjacent, E0Y, right? And it would be the inverse tan, that would be the tilt angle. Do you all follow me? So it's basic trig, and don't worry about that. You can see, obviously, if E0x was 0, it's all in the y direction. Or if E0y was 0, it's all in the x direction. And it would be linear polarization no matter what. Now that is if the phase angle is 0. If the phase angle changes, and let's make it 90 degrees to show you. So if it's 90 degrees, then what happens? Matter of fact, let me do it this way, so it'll be circular, not elliptical polarization. I'll make E0x equal to E0y equal to 1. I want to just reduce the amount of work I have to do. This is same magnitudes in x and y direction. And now if the phase angle is 90 degrees, I'm plotting cosine of omega t ax, right, plus cosine of omega t plus 90 degrees ay. Now work with me on this one. Let's plot that over here. I'll let you see it. So now, I always start off with omega t is 0. When omega t is 0, the cosine, the first part is just going to be 1. Cosine of omega t is going to be, cosine of 0 is 1. You all agree with that? So in the x direction, or for ex, call that y, I've got this point, 1. Come over here for the y component, I have cosine of 0 plus 90. Cosine of 90 is 0, right? Right? So now this is my first point period. This is the vector. All right? Now increase the actual value of omega t. When omega t is equal to pi over 4 or 45 degrees, now what happens? Well, I get cosine of 45 is 1 over square root of 2, about 0.707, right? So in the x direction, now I have 0.707. In the y direction, what happens? Now remember, cosine of 90 is 0, right? Cosine of 135 is negative, right? Isn't it? Negative 0.707. Follow me? So all of a sudden, the y direction is down here. Now it's minus 0.707. That means the tip of that vector has gone from here, 0.1 to 0.2, right? You all see this? And if you trace that out, go ahead and add another 45 degrees so that omega t is 90. You'll see the tip come down here, and you can see it's rotating this way. Can you all see that, class? You just couple of points, plot them, and see where the tip goes. All right. It's positive z direction, it's propagating, so if it's going, that's the positive z direction. For right-handed, it would have to be going this way. You all follow me? It's going the opposite direction. That's left-hand circular polarization. How many see that? You try these things, you'll see how easy it is. So this would be left-hand circular polarization. How many just guess on this one? What's your gut feel if I made this minus 90? Right. Yes. It'll be the opposite. As a matter of fact, the only way to do these, don't try to memorize the stuff he has in the book where he has all these little simple tricks. Just plot the thing. I could put the phase angle in here, couldn't I? Right? I could put it in this one, not that one. What else could I do? I could make that a sine instead of a cosine. It doesn't matter about the trig function or what the angle of displacement is. You plot 2 or 3 points. That's the x, that's the y coordinate. Plot them up there, follow how that tip travels. If it's going counterclockwise, you know it's going to be, I mean, if it's coming out of the board in the z direction, it's going counterclockwise, it's left-handed. If it's going clockwise, it's right. Y'all follow me? Did I say that right, please? Backwards, sorry. If it's going counterclockwise, it's right-handed. If it's going clockwise, it's left-handed. Am I out of time? Not quite. All right, I didn't even get to my other thing, but that's polarization in a nutshell. On Friday, I will do the reflection stuff, normal incidence and reflection, and what we're going to do, we're going to have a quiz Friday. So for the quiz Friday, since this class is so loaded, I'll probably have 2 different quizzes. Like the first row will get one, the second row will get the other, and stuff like this. And it's a closed book, closed notes. You get your calculator. It will be on the material for the last 2 or 3 homeworks. If I was you, I'm not even going to put polarization on. I have to look at the stuff before then, all right? So I'm trying to be as fair as I can. Yeah.
What homework will cover?
The homework from the past couple of lectures, they're all posted on OneNote. You all know what I'm talking about? I mean, understand that. It's the homework on OneNote.
So that will include the power stuff.
Yeah, oh yeah. But not polarization. I'm not going to give that. By the way, polarization is just irritatingly simple, but people foul up because
Just plug in the trig functions.
I can tell you stories about silliness that I see with that. They don't know how to plot cosine. I know.
I'll just be going tomorrow.
Are you talking about my office?
For controls,
John Ho.
Geiger now.
Daniel Geiger, okay.
Yeah.
I think he'd be all right. Controls is actually good. It's a lot of cost transforms and stability.
You'll be teaching radar in the spring, right?
Yeah, I'm looking forward to that. And thank you again for doing that, Miss Eric.
Of course.
Cindy, what are you doing?